Second video on optimization. I've got a problem here that is in the handout on calculus applications, so I'm going to work through this one, and the rest of the problems that are in here I'm going to look for you to work through. So this one here is one of my favorite optimization problems, and I often use this example because this problem just can't be done without a little bit of algebra to start with. So what we're trying to do is find this point here, which is called the Steiner point in a triangle. It's the point that minimizes the distance of AD, DB and DC. So we've got three towns A, B and C. We're trying to construct a road network so that the lengths of those roads are minimized, and what we want to know is where to put D along this line from A to the midpoint of BC. Where do we put that line D? So there's my starting point, and without that bit of algebra there, that's this whole problem, you wouldn't be able to do it. So we're going to start there, calling that little bit there X. What we want to now do is get expressions for the lengths of those three roads in terms of X, and then use calculus to minimize that total distance. You can imagine this is a pretty important problem. These roads are going to be very long. There's a lot of cost involved in making the road, so we want to make sure we get the right point. It's going to save us thousands, if not tens of thousands of dollars to minimize the length of the roads in terms of materials and labor, etc., etc. Okay, so let's look at this triangle here. Once we draw that point there to M, we now know that B to M is going to be 30 kilometers. And you can see these numbers are quite nice. B to M is 30, B to A is 50, which means that the whole length from A to M must be 40, because that's a 3, 4, 5 triangle. So then I can define the length of A to D to be 40 minus X. Yeah, adding those two together gives us 40. So that's helpful as well. So we've got the length of A to D, that's 40 minus X. That's nice. Now we want an expression for the length from D to B. Bit of Pythagoras will tell you that this is the square root of x squared plus 30 squared. Similarly, D to C will also be the same length. So where does that leave us? The total length, therefore, or sorry, the total distance of those three roads is 40 minus x plus 2 lots of root x squared plus 30 squared. Okay, hopefully you can see from the diagram how I worked all that out. Alright, good. So what we want to do now, of course, is we want to find the derivative. So we're going to do dt dx, the derivative of t with respect to x. So minus 1 plus 2. So root x squared plus 30 squared is x squared plus 30 squared to the power of a half. So we're going to have a half x squared plus 30 squared, which is just 900, to the minus a half times by the derivative of x squared plus 900, which is 2x. Okay, so let's tidy all this up. 2 times a half, so those 2's are going to cancel there. So then what are we left with? We've got 2x on the top line, and on the bottom line we've got the square root of x squared plus 900. Okay, so just go ahead now and see if you can solve that equation there. Find the value of x, so that using your calculator or whatever, some algebraic processes, to find the value of x so that that is minimized. Okay, how'd you go? Here's what it looks like. I've got 2x over root x squared plus 900. Of course, if you're using if you're in the calculator section here, this is real easy. You can just use the solve function, so it makes life a lot easier. 2x is root, 900, x squared plus 900. Square both sides gives me 4x squared equals x squared plus 900. This is working out quite neat. 3x squared is 900. X squared must be 900 divided by 3. So x must be the square root of 300. Don't need to consider negative the square root of 300. That just wouldn't make sense at all in this context of this problem. So the square root of 300, just to give us an idea of what that is about 17.32. In this case, it's kilometers. Okay. So that's where we'd put x. Now, what I haven't done in this problem is show or prove that that actually gives us a minimum value. I could do that by considering the second derivative and substituting 17.32 in, or I could just look at the first derivative, that is this function here, and look at what's happening either side. So I could put 17 into here for x, put 18 in, look at the difference. If you did that, you'd find that the gradient would be negative before 17, positive after 17, showing that that value that we've got, 17.32, actually is a local minimum value. So there you go, that's that problem solved.